Welcome to Teolumen Insights, where we reveal the hidden forces that shape the way you live and show you how to use them to create real transformation and supercharge your health, mindset, and daily life. Here are your hosts, Emma Greenwood and Nathan Sinclaire.
Welcome back to Teolumen Insights.
Yeah.
You know, today we're going to be looking at something pretty wild.
Oh, yeah.
Faster than light communication.
Wow.
Imagine like sending a message across galaxies like that.
In an instant.
Yeah. We've got a whole bunch of research papers, articles, even some historical perspectives to kind of dig into today.
Okay.
So yeah, buckle up. I think this is going to be a fun one.
It's amazing, this idea, right? It's been around for so long.
Yeah.
Reaching for the stars, exploring new worlds. It seems like it's just, built into us somehow.
Right.
And while actually traveling faster than light might be a long way off.
Yeah.
Communicating that fast
Yeah.
opens up a whole other realm of possibilities.
Yeah. So let's kind of map out our journey today. We're essentially looking at a whole bunch of wild concepts from theoretical physics.
Okay.
And they all have this one goal.
Okay.
Figuring out if and how we might be able to send information faster than light. Where do we even start with something this complex?
Well, I think a good place to start would be with one of the most talked about ideas.
Okay.
Tachyons.
Okay, tachyons, yeah.
These are hypothetical particles, right?
Right.
But the thing is that according to everything that we know about physics so far,
Right.
they always travel faster than light.
Hold on. Always faster.
Yeah.
That kind of goes against everything we know about the speed of light being like the ultimate speed limit.
I know. It's wild.
Yeah.
But Einstein's theory of special relativity actually allows for the possibility of particles
Oh, okay.
that have what we call imaginary mass.
Okay.
And these particles, if they exist, would always be traveling at superluminal speeds.
Imaginary mass. Okay, so not negative mass. We've talked about negative mass before.
Right.
This is something else entirely.
It's a mathematical concept.
Okay.
But a research paper from 2002 suggested that creating tachyon pairs might not require a crazy amount of energy. Like, it could be comparable to the energy needed to create regular particles, which we call bradyons.
So you're saying we wouldn't need like a supernova to create these things.
Right. Potentially. If, of course, they exist. This is all theoretical.
Right.
There are still big challenges and paradoxes to work through when it comes to tachyons.
Oh, like what?
For instance, how do you avoid those time travel paradoxes where you send a message back in time and change the past?
Yeah, those always get me. That's confusing stuff.
Right.
So where do we even begin to tackle those problems?
Well, there have been a few attempts to reconcile tachyons with our current understanding of physics.
Okay.
And one of those is called the generalized Lorentz transformation, or GLT.
Okay.
It's a mathematical framework that's attempting to sort of fit tachyons into the bigger picture.
Right.
It gets pretty complex, but the takeaway is that scientists haven't ruled out tachyons entirely.
Right.
They're actively looking for ways they might fit into the universe as we know it.
Okay. So tachyons. Weird, bizarre, but still on the table.
Yeah.
But I'm guessing that's just the tip of the iceberg when it comes to faster than light communication ideas.
Yeah, absolutely. Our sources point to, some really interesting concepts.
Okay.
One that really caught my eye is this idea of intergalactic modems.
Intergalactic modems. Okay, that sounds like straight out of like Star Wars.
Yeah.
But how could those even work? If we're talking about like communicating across these unimaginable distances.
Right.
How is that possible?
That's the exciting part.
Okay.
We have to be open to the possibility that there are fundamental principles of the universe that we still don't grasp.
Right.
And that these principles could revolutionize our understanding of communication.
So are these intergalactic modems basically just like a placeholder for whatever crazy physics we might find in the future?
Yeah, I think so. I think it's like a challenge to ourselves to figure out how to make the seemingly impossible possible.
I love that.
Yeah.
So speaking of pushing the boundaries, we've got to talk about quantum entanglement. That spooky action at a distance.
Right.
Where two particles are linked no matter how far apart they are.
Yeah.
Like, that's always blown my mind.
Yeah, it's one of the most fascinating parts of quantum mechanics for sure.
Yeah.
But there's a catch.
Yeah.
While entanglement allows for this seemingly instant connection between particles.
Right.
It doesn't actually allow for faster than light information transfer.
Wait, what? How? If these two are linked,
Right.
why can't I change one and then the other one reacts instantly, regardless of distance?
Here's the tricky part. The way we measure entangled particles introduces randomness.
Okay.
We can't control the state that we observe when we measure one of the particles.
Right.
And that randomness means we can't use it to send a specific message.
Okay, so it's spooky, but it's not a communicator.
Not directly, no. But there's a concept that that researchers are exploring called the entanglement bosonic channel.
Entanglement bosonic channel.
Yeah.
Okay.
This involves sort of manipulating entanglement in a way that could potentially allow for controlled information transfer.
So we're not giving up on entanglement just yet.
No, definitely not. I mean, look at all the entanglements in quantum communication that use entanglement for, secure data transfer and things like that.
Right.
That's a booming field, and discoveries in that field could have really major implications for how we understand and utilize entanglement.
Mm-hmm.
Maybe even for faster than light communication.
Okay, so we've got tachyons, we've got these intergalactic modems that rely on yet to be discovered physics, and then we've got the potential of entanglement. What other crazy stuff are we diving into today?
Well, get ready for this. We're going to explore the mind-bending concept of manipulating space-time itself.
Space-time manipulation. Now we're talking. This is where we bring in the wormholes, the warp drives, all that.
You got it. The idea here is to find ways to warp or distort the fabric of space-time.
Okay.
To, create shortcuts, tunnels.
Yeah.
That could allow for faster than light travel or communication.
Okay, even for me, this is where things start to get a little too sci-fi.
Right.
Is this even remotely possible?
It's definitely pushing the boundaries, but wormholes, for example, they are theoretically possible.
Oh, okay.
According to Einstein's theory of general relativity, the problem is they would require something called exotic matter.
Exotic matter.
Matter with negative energy density to keep them open and stable.
Negative energy density. That's even weirder than imaginary mass.
I know, right?
Have we found any evidence that exists?
Not yet.
Okay.
But the search continues.
Right.
Now, besides wormholes, there's another really fascinating concept called quantum slipstream.
Quantum slipstream.
That also involves manipulating space-time.
Okay.
But in a different way.
So how does that work?
Imagine creating a distortion in space-time.
Okay.
A kind of tunnel that allows information to basically bypass the usual speed limits of the universe.
So instead of trying to travel through space faster than light, we're manipulating space itself to create shortcuts for information.
Yeah, exactly.
That's why.
It's like folding a piece of paper to bring two distant points closer together.
Right.
But of course, we're talking about folding the very fabric of space-time, which would take a massive amount of energy and control over the fundamental forces of the universe.
I can only imagine. So we've got wormholes that need this hypothetical exotic matter.
Right.
We've got quantum slipstream, which sounds just as wild.
Yeah.
What else? What other approaches are there?
Oh, there are plenty more, and they get even more mind-bending from here. One that really stood out to me was the idea of manipulating the space-time metric itself.
Okay, hold on. Break it down for me. What do we mean by the space-time metric?
Think of it as the mathematical framework that defines the very fabric of the universe. So the distances, the time intervals, the relationships between them.
Right.
It's what gives rise to gravity, that curvature of space-time around massive objects.
So manipulating the space-time metric, we're talking about altering the very structure of reality.
Yeah, kind of.
That's a heavy concept.
It is. But theoretical physicists believe that by precisely manipulating this metric, we could potentially create pathways for information to travel faster than light.
That's incredible.
Yeah.
But how? How would we even begin to manipulate something as fundamental as that?
Well, that's where things get really, really futuristic.
Okay.
Our sources mention something called space-time coding digital metasurfaces.
Space-time coding digital metasurfaces.
Essentially, these are engineered material that are designed to interact with electromagnetic waves like light in incredibly precise ways.
So we're talking about materials that can like bend and twist and manipulate light itself.
Yeah.
And by doing so, they can manipulate the space-time metric.
Precisely. Imagine a metasurface that can create a localized distortion in space-time.
Okay.
A kind of warp bubble, if you will.
Warp bubble.
Yep.
See, now we're back in Star Trek territory.
Oh, you know.
Okay, but this sounds insanely complex, even more so than wormholes or quantum slipstream.
It definitely is. And it's important to remember that we're talking about highly speculative technologies here.
Right.
Things that might be centuries or even millennia away.
Right. But exploring these possibilities, even if they seem crazy, helps us like push the boundaries of understanding and imagination.
Absolutely.
What other space-time bending concepts are out there?
Well, one that really caught my eye was the idea of a galactic center rotating beacon.
Galactic Center rotating beacon. Okay.
So imagine a beacon.
Okay. Situated at the very heart of our galaxy, the Milky Way.
Right.
Emitting signals that could travel faster than light.
A beacon at the center of the galaxy. Ambitious. But how could a signal from that far away, reach us faster than light?
The key here is that the beacon wouldn't be transmitting signals in the conventional way.
Okay.
It'd be manipulating the space-time metric itself.
Okay.
Creating ripples or distortions that could carry information at superluminal speeds.
So it's not that the signal itself is moving faster than light. It's that we're manipulating the very medium through which the signal travels.
Yeah, that's a great way to think about it.
Okay.
It's like creating waves in a pond.
Yeah.
The waves themselves don't move faster than the speed of sound in the water.
Right.
But by cleverly manipulating the shape of the pond, you could make waves reach certain points faster than others.
Okay.
So this beacon would be doing something similar. I love that imagery. It really helps to make sense of something that's so hard to wrap your head around. So what other ways are there to manipulate space-time for communication?
Well, here's one that might seem a bit more down to earth.
Right.
Even though it still deals with some pretty crazy concepts, periodic pulse trains and superluminal signals.
Periodic pulse trains. Okay, I'm intrigued.
Yeah.
How do those tie into faster than light communication?
So researchers have been exploring how specific patterns of light pulses,
Right.
these periodic trains, might appear to travel faster than light.
Okay.
It's not true FTL travel, but it creates a really convincing illusion.
An illusion. So it would look like something's moving faster than light, even though it's not.
Exactly. It has to do with the way these pulses are arranged.
Okay.
And how our instruments interpret the signal. So imagine a series of light pulses, each arriving at a detector slightly delayed from the previous one.
Okay. Yeah, I can picture that. So how does that create the illusion of faster than light speed?
Well, it all comes down to the timing.
Okay.
If the delay between the pulses is just right, the overall shape of the pulse train can appear to shift forward in time as it travels.
Okay.
Giving the impression that it's moving faster than light.
So it's like an optical illusion, but on a cosmic scale?
Yeah, exactly.
That's amazing. Even if it's not true FTL travel, could this have any practical application?
That's what scientists are investigating right now. It's possible that these superluminal pulse trains could be used for really high-speed data transmission.
Okay.
Or even for creating new kinds of imaging technologies.
Wow. So another example of how exploring even the most theoretical concepts can lead to real-world breakthroughs.
Absolutely.
That's so cool.
And speaking of pushing the boundaries, we can't forget about quantum tunneling.
Oh yeah, quantum tunneling.
This is something that's been experimentally verified. Right. And it raises some really deep questions about causality and the limits of information transfer.
So quantum tunneling, that's where a particle can pass through a barrier that it shouldn't be able to, according to classical physics.
That's it. It's like a ghost walking through a wall.
Yeah.
Now, while tunneling itself doesn't actually involve exceeding the speed of light,
okay,
it does challenge our conventional ideas about how information can be transmitted.
Okay, how so? If it can tunnel through a barrier, doesn't it just disappear on one side and reappear on the other instantly?
That's the heart of the mystery. So imagine a particle tunneling through a barrier.
Okay.
From our perspective, it might seem as though it vanished on one side.
Yeah.
And reappeared instantly on the other.
Yeah.
As if it traveled faster than light.
Right. So even though it's not actually exceeding the speed of light, the effect might be indistinguishable from faster than light travel.
Exactly. And that raises, some really profound questions.
Right.
Like, does this mean we can send information faster than light
Right.
without actually breaking any laws of physics?
Right.
What does it mean for our understanding of cause and effect if things can seemingly happen instantaneously?
Whoa. Okay, so some big questions there.
Big question.
Yeah, it sounds like we've only just scratched the surface of what quantum tunneling could tell us about the universe.
Yeah, we've only just begun.
Wow.
And there's another fascinating concept that ties into this, and quantum entanglement.
Yeah.
The entanglement bosonic channel.
Oh, right. You mentioned that earlier.
Yeah.
So this is where researchers are exploring ways to manipulate entanglement.
Right.
To potentially enable faster than light communication.
Exactly. It's a concept that could really revolutionize our understanding of communication.
Right.
And maybe even our place in the cosmos.
Okay, so entanglement bosonic channel. What makes this so special, in this whole quest for faster than light communication?
Well, the really cool thing about this idea is that it uses the strange nature of entanglement, right, to create a communication pathway.
Okay.
That might, sidestep those pesky speed of light limitations.
Okay, so walk me through it. How does this channel actually work?
Okay, so imagine two entangled particles.
Okay.
Right, separated by a huge distance, maybe light years even.
Okay, yeah.
Now, instead of trying to directly change one particle to send a message to the other,
Okay.
we bring in a third particle, a boson.
A boson. Now remind me, what exactly is a boson again?
Think of bosons as the carriers of fundamental forces.
Okay.
So light, for example, is made of photons.
Right.
And photons are bosons that carry the electromagnetic force.
Okay, yeah.
In this case, the boson acts kind of like a middleman between those two entangled particles.
Okay, so we've got our entangled pair and then this boson hanging out in the middle.
Right.
How do we use those to actually transmit information?
Okay, so by carefully controlling how the boson interacts with one of the entangled particles, we can influence the overall entangled state of the whole system.
Okay.
It's kind of like subtly changing the tension in a rope.
Oh.
That connects two distant points, right? The rope itself isn't carrying information.
Right.
But that change in tension, right,
Yeah.
is felt at both ends simultaneously.
Okay, I like that analogy. That's helpful. But I'm still struggling with, what makes this bosonic channel potentially faster than light?
Right.
Isn't everything still limited by the speed of light?
Well, here's the key.
Yeah.
The interaction between the boson and the entangled particle doesn't have to travel through space at the speed of light.
Okay.
It's a quantum interaction
Okay.
happening within the framework of entanglement, which operates, outside of our usual understanding of space-time.
So we're essentially finding a loophole in the speed limit of the universe.
Yeah.
By using, the weirdness of quantum mechanics.
Yeah.
Pretty neat.
It is pretty neat. Of course, this is still highly theoretical.
Right.
There are massive technological hurdles to overcome.
Sure.
I mean, we need to perfectly control entanglement, manipulate bosons at the quantum level,
Right.
and shield the whole system from decoherence, which is kind of like the noise that can disrupt those delicate quantum states.
Yeah.
It's a big task.
I can imagine the engineering headaches that would involve. But if we could pull it off,
Right.
the possibilities are incredible. I mean, instant communication across the galaxy,
Yeah.
revolutionizing space exploration,
Absolutely.
scientific collaboration. It would change everything.
It would change everything. It's a very tantalizing prospect,
Yeah.
for sure. It really highlights the transformative potential of quantum mechanics.
Absolutely. So, speaking of pushing the boundaries, earlier we were talking about quantum tunneling.
Right.
That thing where a particle can pass through a barrier even if it doesn't have the energy to do so.
That's the one. And while quantum tunneling itself doesn't break the speed of light,
Right.
it does make us question, how information can be transmitted.
Okay.
And what the true limits of cause and effect might be.
Okay.
It's a really wild concept.
Explain it to me like I'm 5.
Okay.
How does a particle tunneling through a barrier challenge our understanding of information transfer?
Okay, so imagine a child
Okay.
trying to roll a ball over a hill,
Okay.
right? If the ball doesn't have enough energy,
Yeah.
it'll just roll back down.
Right.
But in the quantum world, that ball has a chance of suddenly appearing on the other side of the hill,
Okay.
as if it tunneled right through.
Yeah.
Now imagine if we could somehow attach information to that ball
Okay. Yeah.
and it tunneled through the hill.
Right.
Wouldn't it seem like the information traveled instantly?
Yeah, it would.
Even though the ball didn't technically move faster than anything else?
So even though nothing is exceeding the speed of light,
Right.
the end result, it would be indistinguishable from faster than light communication.
Exactly. And this raises, all sorts of questions.
Like what?
Like, does this mean we can send information faster than light without actually breaking any laws of physics?
Right.
What does it mean for our understanding of cause and effect if things can seemingly happen instantaneously?
Those are some seriously deep questions.
Yeah, they are.
Wow. But before we get too lost in the philosophical weeds, there's a couple other FTL concepts we haven't really touched on yet.
You're right. There are a few more, and each one is just as mind-bending as the last. For instance, there's this idea of using periodic pulse trains to create superluminal signals.
Okay, back up for a second.
Yeah.
What are periodic pulse trains, and how could those be used for faster than light communication?
Essentially, it's all about using carefully timed pulses of light to create an illusion of superluminal speed.
Okay.
So imagine a series of light pulses being emitted, each one slightly delayed from the one before it.
All right, I'm picturing it. So how do we make those pulses look like they're moving faster than light?
It's all about the arrangement and the timing.
Okay.
If we get those just right.
Right.
The overall shape of the pulse train can appear to shift forward in time as it travels.
Okay.
It's kind of like a wave on a rope.
Right.
The wave itself isn't moving faster than the rope.
Right.
But the shape of the wave can change in a way that makes it look like it's moving super, super fast.
So it's a bit of like an optical illusion, but on a cosmic scale?
Yeah, exactly.
That's pretty wild.
Yeah.
But even if it's not true FTL travel, could this have any practical applications?
That's what researchers are trying to figure out. It's possible that these superluminal pulse trains could be used for transmitting data at really, really high speeds.
Okay.
Or even for developing new types of imaging technology.
Wow. That's amazing. Like, we could see things in ways we never thought possible.
Exactly.
That's incredible. But I have to admit, my brain's starting to feel a little bit full.
I know, I hear you.
Just a little bit overloaded with all these concepts.
It's a lot to take in. But that's the beauty of exploring, these frontiers of science.
Right.
It really challenges our understanding of what's possible. It opens up these whole new realms of imagination.
Okay, one more mind-blowing concept before we take a break.
Okay.
What else do we have?
How about manipulating the space-time metric itself to create what are essentially warp bubbles?
Warp bubbles. Okay, now you're talking. But how could we manipulate something as fundamental as the fabric of space-time?
That's where things get really futuristic.
Okay.
We'd need to develop what are called space-time coding digital metasurfaces.
Space-time coding digital metasurfaces. Okay. Wow.
These are essentially advanced materials that can interact with light in incredibly precise ways.
So we're talking about like materials that can manipulate light itself.
Yeah.
And by doing so, they can actually warp space-time.
Precisely. So imagine creating a small localized distortion in space-time.
Okay.
A warp bubble.
Warp bubble. Okay.
That would allow information to essentially bypass the speed limits of the universe.
That sounds like Star Trek.
I know.
But how realistic is this? Are we talking about something that's centuries away?
It's definitely on the far end of speculative technology, but that's the beauty of theoretical physics. We can explore these possibilities even if they seem, impossibly far off.
Yeah.
Who knows what incredible breakthroughs are out there waiting for us.
That's true. Okay, one more question before we wrap up this section. What about that idea of a Galactic Center rotating beacon?
Oh, yes. Now that concept is truly mind-boggling. So imagine, a beacon situated at the very heart of our galaxy, the Milky Way,
right,
emitting signals that could travel faster than light.
So essentially a cosmic lighthouse, like guiding us through the vast expanse of space.
Exactly.
That's an awesome image. But how could a signal from that far away reach us faster than light? And how would we even build something like that in the first place?
Well, that's where things get really interesting. This beacon, it wouldn't be sending out like traditional signals.
Okay.
It would be manipulating the very fabric of space-time,
Okay.
creating ripples and distortions that could carry information at superluminal speeds.
So we're not talking about a radio wave or a laser beam or something. We're talking about like manipulating the universe itself.
Exactly. It would be like creating waves in a pond, right? The waves themselves don't move faster than the speed of sound in
Tachyons.
water.
Right.
But by cleverly manipulating the shape of the pond,
Yeah.
you could make waves reach certain points faster than others.
Right.
This beacon would be doing something similar, but with space-time itself.
That's absolutely amazing.
Yeah.
But building something like that just seems almost incomprehensible.
It's definitely on the extreme end of speculative engineering. but remember, even the most outlandish ideas, right?
Yeah.
They can inspire new avenues of research.
Right.
Lead to unexpected breakthroughs.
Right.
The journey of scientific discovery is all about pushing the boundaries of what we think is possible.
Well, you've definitely pushed the boundaries of my imagination today. We've covered so much from tachyons to wormholes to manipulating the very fabric of space-time.
Yeah.
Before we move on, though, there's one last concept I want to touch on.
Okay.
Quantum transceivers and receivers.
Ah, yes.
Yeah.
Quantum transceivers and receivers.
So these are theoretical devices that could revolutionize communication.
Especially when paired with some of the other concepts that we've been talking about, like quantum entanglement.
Okay, so tell me more. How do these transceivers and receivers work? How could they be used for faster than light communication?
Well, the basic idea is that these devices would be designed to encode and decode information.
Okay.
That's being transmitted through quantum channels.
Okay.
So, for example, imagine using a quantum transceiver to send a message via that entanglement bosonic channel we talked about earlier.
So we'd be using entanglement as the medium.
Right.
And these transceivers would be like the phones on either end of the line.
Yeah, that's a great way to put it. So the transceiver on the sending end would encode the message into the quantum state of a particle.
Okay.
And the receiver on the other end would be able to decode that information, even if those particles are separated by vast distances.
Okay. But wouldn't we still face like those challenges with entanglement that we talked about earlier?
Yeah.
Like the randomness of measurements and the difficulty of controlling those delicate quantum states.
Absolutely. Developing quantum transceivers and receivers that can reliably operate over long distances. I mean, that would be a massive technological challenge.
Right.
We need to overcome issues like decoherence.
Right.
Find ways to amplify those really, really faint quantum signals. It's a big task.
So we're talking about some seriously advanced tech here.
Yeah.
Is this something that's even like remotely feasible right now?
It's definitely pushing the boundaries of what we can currently achieve.
Right.
But remember, even just a few decades ago, things like quantum computers, quantum communication networks, I mean, these were considered science fiction.
Yeah.
The pace of progress in this field is just astounding.
That's true.
So who knows what incredible breakthroughs are waiting for us in the coming years.
I'm excited to find out.
Yeah.
But I think we've covered enough groundbreaking concepts for one episode.
I agree.
You know, we've journeyed from the theoretical realm of tachyons to the mind-bending possibilities of space-time manipulation and quantum entanglement.
We've explored the potential of intergalactic modems, Galactic Center Beacons, quantum transceivers, each one pushing the limits of what we know about communication and the universe itself.
It's amazing to me that all these concepts that we've been talking about, as wild as they are, you know, they're all rooted in actual science.
Yeah.
It really makes you wonder what the future holds, you know?
It does, not just for communication, but for our understanding of the universe as a whole.
Exactly. And you know, exploring these possibilities, even if they seem really far-fetched right now, it can lead to all sorts of unexpected discoveries, you know,
right,
and advancements in other areas.
It's like you set off on this expedition to find a new continent.
Okay.
But then you stumble upon this hidden valley,
right,
filled with wonders that you never even imagined.
Yeah, I love that. But after going through all this, I have to ask, you know, if faster than light communication were to become a reality, what would it mean for us?
Yeah.
Like, wouldn't that just fundamentally change our understanding of the universe, our place in it?
That's the ultimate question, isn't it? I mean, if we could truly send information faster than light, it would have some really profound implications for how we understand causality, you know? The very notion that cause must come before effect.
Yeah, it would kind of turn our understanding of time upside down, wouldn't it?
Yeah, I mean,
if we could send messages back in time, even if it's just information and not like physical objects,
right?
Wouldn't that lead to all sorts of paradoxes and contradictions?
It's a tough one to wrap your head around, for sure. I mean, imagine being able to send a message to your past self, you know, potentially changing the course of events.
Right.
It really challenges our fundamental understanding of the flow of time.
Yeah.
And the nature of reality itself.
It's a bit overwhelming to think about, honestly. but that's what I love about these deep dives.
Yeah.
They force us to confront those limits of our knowledge.
Yeah.
And consider possibilities that seem both exhilarating and terrifying at the same time.
Absolutely. I mean, these explorations, they remind us that the universe is just full of mysteries, and our understanding of it is constantly evolving.
Right.
What seems impossible today, I mean, it might be commonplace tomorrow.
So you mentioned earlier quantum tunneling.
Yeah.
That it raises some questions about cause and effect.
Right.
Even though it doesn't, technically involve exceeding the speed of light.
Right.
Could you kind of elaborate on that a bit more?
Sure. Quantum tunneling is one of those phenomena that really highlights just how strange quantum mechanics can be. Right? So a particle can seemingly pass through a barrier instantly.
Yeah.
Even if it doesn't have enough energy to do so according to, classical physics.
It's like that child rolling a ball over a hill and then suddenly it's just on the other side.
Exactly.
Even though it never went over.
Yeah. Yeah. Now imagine that we could somehow encode information onto that ball.
Okay, yeah.
Right. When the ball tunnels through the hill,
right,
it would appear as if that information traveled instantly.
Yeah.
Even though the ball itself didn't, exceed any speed limits.
So it's not that anything is actually moving faster than light, but the effect is essentially the same.
Right.
Instant transmission of information.
Exactly. And this raises some really fascinating questions about causality.
Like what?
Well, did the information truly travel instantly? Or is our understanding of cause and effect just incomplete?
Yeah.
Does quantum tunneling point to some deeper connection between distant points in space and time?
It makes you wonder if there are like hidden layers of reality that we're just now beginning to glimpse.
I think so.
Yeah.
And that's what makes exploring these concepts so exciting. They force us to question those assumptions,
right,
and push those boundaries of what we think is possible.
Okay, so one last thought before we wrap things up here.
Okay.
We've talked about all these incredible possibilities.
Yeah.
But are any of them like actually achievable?
Right.
Is faster than light communication something that we could realistically see in our lifetime?
That's the million-dollar question.
Yeah.
And while we've made some incredible strides in our understanding of physics and technology,
right,
FTL communication, I think it remains firmly in the realm of theoretical possibility.
Okay.
The technological hurdles, they're immense. And we're still really grappling with the fundamental implications, of what it would mean for our understanding of the universe.
So we're not quite ready to send messages across the galaxy at warp speed just yet.
Not quite, no. But that doesn't mean we should stop exploring these ideas. I mean, the pursuit of knowledge is a journey, right?
Yeah.
Every step we take, even if it doesn't lead us to that ultimate destination, it expands our understanding. It opens up new possibilities.
I couldn't agree more. This deep dive has been an incredible journey through the frontiers of theoretical physics. We've covered so much.
Yeah.
From tachyons to wormholes to quantum entanglement.
It's been a real pleasure exploring these mind-bending concepts with you.
Likewise.
And to all our listeners out there, I just encourage you, keep those minds curious and keep exploring those wonders of the universe.
Yeah.
Who knows what amazing discoveries await us just around the corner.
Well, that brings us to the end of another fascinating episode of Teolumen Insights.
Yeah.
Thanks for joining us on this deep dive into the truly mind-blowing possibilities of faster-than-light communication. Until next time, keep exploring, keep questioning, and keep wondering about this incredible universe that we all live in.